Hi, this is Professor Stugard, and in this video we're going to keep talking about double integrals, but what we're going to look at this time are going to be double integrals over regions that are better described by polar coordinates than by our typical rectangular or Cartesian coordinates. So to start, let's actually start with an example to kind of explain what kind of problems would be better tackled with this particular technique. So let's say I want to evaluate this double integral over the region D of 2xy dA, a pretty standard double integral, except our region D is given by the expression x squared plus y squared being bounded between 4 and 16. And then we also have x is greater than or equal to 0 and y is greater than or equal to 0. Now, no matter what, the first step is always going to be to sketch and understand the region we're trying to integrate over. Now, I graphed this for us already, but again, take your time, use technology if you need to. But the idea here is that, again, that expression x squared plus y squared, that is how we describe a circle centered at the origin in our xy plane. And again, it goes back to the formula that x squared plus y squared equals r squared. So that x squared plus y squared equals 4 gives me a circle with a radius of 2. X squared plus y squared equals 16 gives me a circle with a radius of 4. And then, of course, the fact that we had that expression x squared plus y squared bounded between them is why we're between those two circles in my xy plane. Then we also have that x is greater than or equal to 0, y is greater than or equal to 0, which means we are bounded in quadrant 1. Now, the thing is, we could try to set up our integral now as a type 1 or a type 2, except it's actually going to be quite unpleasant to try to evaluate that integral, because we're going to have to solve these circles for either y as a function of x or x as a function of y, depending on whether we're doing a type 1 or a type 2. And again, it's just going to be kind of a mess. But as soon as I see circles like this, and really the key thing you're going to be looking for is going to be expressions like x squared plus y squared telling you that, of course, these are circles. This is going to be much easier to do in polar coordinates. Now, let's review polar coordinates quite briefly, because again, hopefully you've seen this before, but polar coordinates are basically how we apply right triangle trigonometry to an ordered pair xy, where instead of discussing the point in terms of how far over and how far up, we discuss it instead in terms of the distance from the origin r, and then the angle that our right triangle would make with our x-axis. Now, like I said before, we have x squared plus y squared equals r squared. Again, that's just our Pythagorean theorem, which of course also describes our circle. And that's how we can relate r to the variables x and y. We also have that theta equals the inverse tangent of y over x. And again, that's just going back to SOHCAHTOA. That one's not going to be as useful for us. I mean, still true, but we're not going to use it all that much. And then the last two, x is r cosine theta and y equals r sine theta. These we are going to use quite a bit as we do polar coordinates and as we continue on through Calculus 3, and we see regions that are better described in polar coordinates. Now, again, each of those x and y's are really just applications of SOHCAHTOA on that right triangle that is in the picture right there. But again, we should be familiar with right triangle trigonometry, and we should be familiar with polar coordinates, so let's talk about the fact of integrating over our polar regions. Now, when we went back and we looked at our first double integrals for continuous functions, when we had our rectangular or our Cartesian coordinates, when we tried to set up that area that we are integrating over, we subdivided that area into subrectangles, each with a dA equal to dx dy. And again, kind of similar to how, right, a rectangle has an area of its length times its width. Right? Now, in polar coordinates, we're going to have to subdivide this region using sectors and using polar rectangles. So let's start with the concept of sectors first. Now, a sector is our portion of a circle that's enclosed by two radii. All right, and the most important formula here is that one from trigonometry or pre-calc that says that the arc length S is equal to the radius times the angle theta in terms of, well, radians. And again, this is calculus. Every angle should be in radians. And again, that's a really nice formula right there, and the proof is fairly simple. And if you don't remember it, go look it up. It's a good one, trust me. Now, how do I find the area of a sector? Well, the sector is just a portion of my circle. We know how to find the area of a circle. The area of a circle is pi r squared. So how do I find just a portion of it? Well, it has to do with that angle theta. It's going to be the ratio of the part to the whole. So we start with our area of a triangle pi r squared, and we need to scale it by, well, how big theta is. Now we know that all the way around the circle is going to be 2 pi radians. So the part to the whole is going to be the part theta to the whole 2 pi, which means my area of my sector is going to be that ratio, or that fraction, theta over 2 pi, the part to the whole, times the area of my circle, pi r squared, and then, well, we cancel out the pi's, and then we kind of simplify, rewrite a little bit, typically, so that we write our area of a sector being 1/2 r squared theta. Now let's talk about polar rectangles. So just like we did when we were doing double integrals over rectangles, and we subdivided everything into subrectangles, now we're dividing them into subpolar rectangles. So we have our region over here, which again is bounded between two angles. Our angle theta is alpha and our angle theta is beta, because again, when we talk about polar coordinates and we talk about angles, again, typically we're going to use alpha and beta. And then again, bounded between two radiuses. In this case, radiuses A and B. And then we subdivide that along those radiuses and our angles theta. Now, if we take one of those really small polar rectangles, like the one there in red, and we look at it much bigger, well, how would I find the area of this? Well, I can approximate the area, right? The approximate area, that delta A, is going to be equal to, well, I take this arc length. And how do I find this arc length? Well, it's that formula that we just looked at, that S equals R times theta. Now, in this case, R is, well, R. And in this case, theta is really delta theta, because that's our change in the angle theta. And then we have our change in the radius as well. And so we're approximating here. It's not exact, but we're saying the approximate area, right, is going to be equal to the length times the width. The length being R delta theta, and the width being delta R. Now, as we move into our infinitesimals, as we start shrinking this down to just infinitesimally small points, well, that approximation becomes exact. And so dA becomes R dr d theta. Now, the really, really important thing to remember here is that, well, we have to include an R when we do this, right? Typically, when we substituted for dA, we substituted dx times dy because, well, that's how we find the area of a typical rectangle. When we're doing this in polar coordinates, you have to include that extra R. All right, that change in area, that polar rectangle, the area of it is found slightly differently. And so you got to be really, 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 really careful. Anytime we switch to polar coordinates, make sure you include that R every time you substitute for dA. And we'll talk a little bit more in depth about why that is and what's going on and what are we doing here. And it turns out this is actually very much related to U substitution in some later sections. For now, it's very sufficient to just make sure you memorize that expression right there, that dA is equal to R dr d theta. So when we do our double integral over a polar region, typically we're always going to bound theta by constants. That's because theta ends up being our independent variable. And it's our independent variable because it's rotation. And it's very, very easy to measure our rotation in terms of constants and in terms of angles, right? Am I rotating from pi over 6 to pi over 3? Well, that becomes my bounds for my integration depending on my polar region. So theta will always be bounded by constants. However, R is typically given as our dependent variable when we're doing polar coordinates. And you can actually see this as well if you put your calculator into polar coordinates and you hit the y equals button, it's going to give you r equals, and then your dependent, meaning your dependent variable is r, and then your independent variable becomes theta. So typically then we have to bound r by two functions of theta. So in this case, h1 and h2 bounds our radius, right? So then when we make our substitution, our function that was originally in terms of x and y now becomes a function in terms of r's and thetas, where again, we substitute every x for r cosine theta, we substitute every y for r sine theta, and then we replace dA with that entire expression r dr d theta. Now, if r is given as a function of theta, that has to go first. Again, any function that has a function of variables must go first. That must be the first of our iterated integrals, whereas anything that's bounded by constants can come last. All right, now we're ready to tackle our example that we started this video with. How do I evaluate this integral? So the nice part is now as a polar type, to describe this polar region, my theta is bounded between 0 and pi over 2 because, well, here's 0 and here's pi over 2. Yeah, that's clearly where we're bounded. That's quadrant 1. And then r is bounded between 2 and 4. And clearly we're stuck between a radius of 2 and a radius of 4. That's that area that I've shaded in. So again, anytime I convert to polar coordinates, that expression x greater than or equal to 0, y is greater than or equal to 0, that's really the same as how I bound my theta. All right. Now in this case, theta is bounded by constants and r is bounded by constants, which is really, really nice. I could apply Fubini's theorem here, but, well, I'm going to kind of stick to the way it's written. So here's my original integral. Here's what I need to do when I make my substitutions. And I'm going to color code this to make it hopefully even easier to see. So obviously it's still a double integral, 2 is a constant, that's fine. But when I make my substitutions, if I'm doing this in polar coordinates, I need to get rid of every x, I need to get rid of every y, and then I need to get rid of my dA. And then my entire problem should be in terms of just r's and thetas, with, again, a dr and a d theta at the end. So we're just going to make the substitution that, well, that we make with polar coordinates. What is x? Well, x is really r cosine theta. What's y? Y is really r sine theta. And then again, like I said, that most important part is that when we substitute for dA, we substitute the entire expression r dr d theta. Now, if you see an x squared plus y squared, well, that's a really nice thing to see in your integrand as well, because x squared plus y squared can always be replaced with just r squared. And again, you can do that with doing, that substitution with x and y separately, and then just, looking for the basic trig identity cosine squared plus sine squared equals 1. But, that's the main idea here, is that, again, my problem now is in terms of just r's and thetas. So let's simplify it a little bit. Clearly, I have an r, and an r, which means I'm really going to have an r cubed. And, well, now I'm ready to integrate. Now, I'm going to integrate the way it's written, of course, because it is bounded by constants, right? Theta is bounded by the constants 0 and pi over 2. R is bounded by the constants 2 and 4. I could use Fubini's theorem to split this up or do this another way, but I'm not going to do that here. I'm just going to factor everything that's not an r and integrate with respect to r first. So again, my only r there is the r cubed. We know that the antiderivative of r cubed is 1/4 r to the 4th. Again, you should be doing this all on your own. So take your time, take the time, pause the video, finish out this integral, and see if you get the same answer as I do at the end. All right, because I'm about to keep going right about now. All right, so again, we evaluate that 1/4 r to the 4th between 2 and 4, which gives me the answer of 60. When I combine 60 with my constant 2 that's in the front, I get 120. And now I need to evaluate the integral cosine theta, sine theta, d theta. Now, there's really two ways to go about this. Some students really like to do the double angle formula, and that's perfectly acceptable because 2 cosine theta sine theta is, well, one of your double angle formulas from pre-calc, from trigonometry. It's a really important one to know and be able to use, and then you can just use u sub from there. Me personally, I would use u sub from the beginning here, and I would set my u to be equal to sine theta, because if this is my u, well, du, the derivative of sine, is cosine. So I would have du as cosine theta d theta. So I literally end up with the antiderivative of u du. The antiderivative of u du is 1/2 u squared. I've changed my limits of integration from 0 and pi over 2, which is, again, my bounds of integration in terms of theta, into my integration in terms of u, which would be 0 and 1, which means that that integral, once I integrate and plug in my bounds, gives me 1/2, and 120 times 1/2 is, well, 60. And again, that's the way I would do it, but you can do it any way you want as long as you get the right answer, 60. And again, as a Calc 3 student, hopefully taking a integral like that one should be almost second nature. All right, so take your time, work on the homework, and again, look for some of those key things in your region. Your region is going to be what tells you that we should do this in polar coordinates. So again, sketching and understanding your region first is the most important thing. And then it's only after you have sketched and understood your region completely that you want to start substituting and writing things in terms of r's and thetas instead of x's and y's. All right, good luck with your homework. If you have any questions, as always, please let me know, and good luck studying.